Morning, good afternoon, depending on what time it is. Um, so this next chapter, we're dealing with different phases of matter, solids, liquids, and gases. And the key things we're going to learn about them is why certain things are solids, liquids, and gases. And you'll see they're basically related to some of the stuff we've been learning about molecular shapes. And you've been wondering, like, why are we learning all these weird shapes and everything, whether things are polar or non-polar? Well, this is the payoff, because you get to understand why certain things are solids, liquids, and gases, and some of the properties that they have, you'll see, are completely related to what shapes they are and the polarity of different molecules. So we're going to define what phase means. We're going to talk about the different kinds of interactions between molecules, because that's the key to this whole thing. How do different molecules interact with each other? That will define whether something's a solid, liquid, or a gas. We'll use different methods to describing the different phases based on what kind of properties their molecules have. We'll see that molecules in gases move really quickly, and they don't really have much interaction with each other, while molecules in the liquid phase have much more interactions between each other and don't move nearly as quickly. And as you can probably imagine, molecules in the solid phase have a lot of very intense interactions, and they will be not moving hardly at all. Of course, we know that molecules continue to move all the way down to absolute zero, but the relative amount of movement in molecules for solids is certainly much, much less than it is for liquids and gases. And then at the end of the chapter, we're going to talk a lot more about gases themselves, because gases have some really interesting properties. And for those of you going to be like respiratory therapists and stuff like that, kind of important to know what properties of gases are, and what happens when we change volume and change pressure and that sort of thing. Is are very, very important relationships for gases. So we're going to talk about intermolecular interactions. INTRA interactions refer to interactions inside of a molecule. So like inside of a molecule of water, an intramolecular interaction would be the interactions between the atoms, hydrogen atoms, and the oxygen atoms. When we're talking about intermolecular interactions, we're talking about interactions between different molecules coming together. So the first thing we want to introduce is the concept of a phase. Now, a phase is just a form of matter that is the same all the way through, has the same physical properties. So solids, liquids, gases. And we know that there's a fourth phase. Anyone know what it is? That's right, plasma. But we're not really going to be talking about plasma, because we don't really see that many plasma phases around. Plasma phase is just basically a gas with charged ionized particles in it, like you would see in a neon sign, for instance, or the sun. The sun is basically a huge plasma. So solids, individual particles can be thought of as they're all in contact with each other, and they're held rigidly in place. Makes sense, right? And then with liquids, individual particles are still in contact with each other, but they have the freedom to sort of move about while still remaining somewhat in contact with each other. And we'll see that that's really important for water. You know, I sort of rave about water all the time being super important. You'll see that water has a certain fascinating interactions in the liquid phase. And in the gas phase, individual particles are completely separated from each other. That's like the biggest difference between the liquid phase and the gas phase. When you heat something, like water, when you're boiling water, In the liquid phase, those molecules are still interacting with each other. And it's those interactions you need to break. That's why it takes energy to boil water. You need to break all those interactions that those individual water molecules are having with each other and then separate them. And then when you've added enough heat to break all those interactions, then the individual water molecules are free to move about without any interaction between them. And that's what a gas is. They're separated from each other and by relatively huge distances. Such huge distances that basically those molecules barely come in contact with each other. They will occasionally collide into each other, but even when they collide into each other, they're not really going to have much contact with each other. Generally, they'll just collide, bounce off each other, and then go off in a different direction. So, whatever phase a substance will take up depends on two things. What kind of pressure is being exerted on it, and what kind of temperature it experiences. Now, temperature changes, we know that basically at 0 degrees, everything becomes a solid because all molecules stop moving entirely. And when the molecules aren't moving at all, you've got a solid. And as you increase the temperature, things have more and more energy given to molecules, and they start to move around. Solids become liquids. And then if you increase the temperature even more, add more heat, liquids become gases. So pressure can also affect the presence of a particular phase. If you take a gas and exert a huge amount of pressure on it, you can convert it into a liquid. For instance, liquid helium, liquid hydrogen, liquid oxygen. All these things are going to be available in the hospital, right? Because all those canisters you see, those gas canisters, don't actually have gas inside. They have some gas inside of them, but most of the oxygen or whatever that's inside there is actually in the form of a liquid, because it's under such huge amount of pressure that basically we are forcing those molecules to interact with each other. And if you force those molecules to interact with each other, then when they start to interact with each other, they start moving less and they convert from a gas into a liquid. And you can see some of the examples here. So water being the classic example, we know that it freezes at 0 degrees Celsius. And so it turns into a gas above 100. Above 0, it goes from a solid to a liquid. And then at 100 degrees, it goes from a liquid to a gas. That indicates the amount of energy needed to be put into boiling water. Now you look at something like sodium chloride, you can see the sodium chloride is held together with much stronger intermolecular interactions, because you need to heat sodium chloride to 800 degrees in order to turn it from a solid into a liquid. So it takes a lot more energy to take something with ions, sodium ions and chloride ions, to separate those so they can move around. It takes a lot more energy than it does for something like water, which has weaker intermolecular interactions. And we'll talk a lot more about those, specifically about water a little bit later. So you wonder why some substances become liquids at really, really low temperatures, like gases, for instance, that we see at room temperature. Nitrogen, for instance, you need to reduce down to like almost 200 degrees below 0 in order to get it to be a liquid, become liquid nitrogen. Why does it take so much more energy to convert some gases to liquids and some liquids to solids, and the other way around. It depends on how strong those interactions are in between them. And this is an introduction to some of them right here. So we've got ionic interactions are pretty much the strongest interactions you're going to find between two particular molecules. Why? Well, because you've got positive and negative charges. And the more positive and negative charges you have, the stronger that interaction is going to be. And so it's going to be really, really difficult to pull those apart. And that is one of the reasons why we see precipitates form in solutions when you have ions with a lot of charge come together, like phosphate I've mentioned before. If you have phosphate with a -3 charge, comes into the presence of an ion like iron 2 or calcium or something that has 2 charges, they form this huge, multi-charged complex that is so stable it just crashes out of solution, because that's a much, much stronger interaction than the ions were interacting with the water. So ionic interactions, basically, number one, as far as intermolecular interactions go, they're the strongest. That's why ionic compounds don't become liquids till extremely high temperatures. Next is hydrogen bonding. And we've talked a little about hydrogen bonding. Basically, it is a special polar interaction that very polar molecules can do, like water, like hydrogen fluoride, like ammonia, that have very, very polar bonds. And you remember what a very, very polar bond is a bond with a big difference in electronegativity. And in this instance, it's a big difference in electronegativity between the hydrogen and the atom that it's bonded to. So if hydrogen is bonded to either oxygen, nitrogen, or fluorine, it forms a very polar bond that interacts more strongly than a typical polar bond. Pause for dogs. Dog drama over. So hydrogen bonding for very, very polar bonds. Next we have dipole-dipole interactions. And dipole, we sort of remember what a dipole is. A dipole is a difference in polarity, difference in electronegativity between two atoms in a bond. And so that is a dipole. And that is for polar molecules that basically can't make hydrogen bonds. So they're polar, yes. They have a slight positive and a slight negative charge, but they're not quite as polar as these hydrogen oxygen, hydrogen fluorine, hydrogen nitrogen bonds. Not quite as polar. So those interact with each other a little less with a little less strength than a hydrogen bond. And last, down here at the bottom, which you can't really see, it's called London dispersion forces. And basically that's the last resort of molecular interactions. That is the molecular interaction or intermolecular interaction that every molecule can do. And I'll talk a little bit more about that later. But basically that is the interaction between non-polar molecules. Even non-polar molecules can interact with each other. And if they have a lot of electrons, if they're like really big molecules, then a lot of very, very weak interactions can be strong enough for these things to stick together. And one of the classic examples we give is candle wax. Candle wax is a non-polar molecule. Paraffin is a non-polar molecule. It's only carbons and hydrogens, so it's about as non-polar as it can get. But paraffin is a huge molecule. And so if you put together a lot of very weak interactions, but a whole bunch of them, that's enough in order to get it to stick together as a solid. Now, one of the very strongest interactions that we don't really talk about, because it's not really an intermolecular interaction as much as an intramolecular interaction, because it's inside a molecule. It's something called network bonding or covalent network bonding. And that is some of the instances where every single atom in a single molecule is connected to each other. And the most given example, the example that is explained the most, is diamond. There's a reason why diamond is the hardest, or one of the hardest. I think scientists are constantly working on something that's harder. But why it's such a hard compound? It's because every atom in a diamond is covalently bonded to other atoms. They're all linked with carbon-carbon single bonds. Now, one carbon-carbon single bond isn't all that strong, but if it connects every single atom in a diamond, then those become extremely difficult to break, because then you would have to break billions of them in order to shatter that diamond or break it in some way. So diamond is really, really hard. You can basically cut anything with it because of the number of bonds you would have to break in order to break that diamond. There are also like certain sands, quartz are network covalent, silicon dioxide. They also form a network. But generally, they're a lot more brittle than diamond, because they have a lot more flaws in them, and they shatter a lot easier. Diamond, they're held together by single bonds, and they're all very close to each other, and so much more difficult to break. Then we have ionic interactions, and we're all familiar with what ions are, hopefully, at this point. So we have an attraction based on opposite charges. So salts, which is basically any ionic compound, we just call it a salt, have really high melting points and really high boiling points. The higher those number of charges, as I mentioned before, the stronger the interaction is. So sodium chloride basically forms a network. You see this network of interactions all the way through, where you have smaller sodium ions next to larger chloride ions, and they form what's called a lattice, where all these charges hold the whole thing together. So you can see that each individual chloride ion isn't binding just one sodium, but a bunch of sodiums around it. And same with the sodiums and the chloride. They're all sort of caged together by opposite charges surrounding it. And so you can imagine that if these are single charges, that would be a certain amount of strength as an interaction. But imagine doubling it. So you take something like calcium oxide. Now calcium is +2 and oxygen is -2. And so basically you have doubled the strength of all those interactions. And so calcium oxide melts at a much higher temperature, about 1,000, I think even 2,000 degrees hotter than sodium chloride, because that is just a strength of a single ion and with a single charge. And then when you have two double charges together, the strength is even greater. Now let's talk about polar versus nonpolar, and we've been dealing with that, talking about shapes. Now, substances that experience covalent bonds generally exist as these discrete molecules. They're not going to be a whole network of interactions. And remember, we have two different kinds of covalent bonds. We have polar and we have nonpolar. The difference being, with a polar bond, they do not share the electrons equally. Remember, fluorine over here is the most electronegative element there is. It will be pulling those shared electrons. Remember, electronegativity refers to the strength of the ability to pull shared electrons toward itself. Fluorine can do that better than anybody. So it pulls those shared electrons toward itself. And fluorine has a relatively high, but not a full, negative charge. Partial negative charge. The hydrogen has a partial positive charge. So this is a very, very polar molecule. Now, nonpolar covalent bonds, they have equal sharing of electrons, like carbon and hydrogen. Their electronegativities are pretty similar. The difference is only around 0.3, 0.4. Very, very small difference. So they share those electrons in their pairs, the pairs that go into a bond, fairly equally. And so you don't really see much of a charge in the carbon or in the hydrogen. So there's not really a dipole there. You don't see a partial positive on the hydrogen and a partial negative on the carbon. There's very, very little difference. And so that polar interaction is very, very weak, and you don't really see a polar interaction at all. Now, the reason we went to looking at shapes is because you remember the shape tells you whether or not the entire molecule is polar or not. Because when we look at, and the classic example I've looked at many times, is carbon dioxide here. Now, the carbon in the middle is less electronegative than the oxygens on the outside. We know that oxygen is like the second most electronegative element there is, right? So that oxygen on that side is slightly negative. That oxygen on the other side is slightly negative. And that carbon in the middle is slightly positive. However, it is completely symmetrical. And so we don't really see the whole molecule being polar. When it's completely symmetric, we basically see that the bonds are polar, but the molecule isn't. And so carbon dioxide basically acts a lot like a non-polar molecule. Although we will see carbon dioxide is a sort of special example, because carbon dioxide doesn't exist in the liquid state unless you force it. And it's because of these bond dipoles that are present. So carbon dioxide that we breathe in and out every day is a gas, but when you cool it, it doesn't turn into a liquid. As you know, it turns into dry ice. It turns into a solid. And it doesn't exist as a liquid unless you put it under a lot of pressure. And so even though we don't have, it's not a polar molecule, it does have some polar properties because of the big difference in charge. And then over here, we have carbon tetrachloride. So tetra, meaning 4, right? Carbon surrounded by 4 chlorines. Chlorine is more electronegative than carbon. And so these chlorines will be slightly negative, and the carbon in the middle will be slightly positive. But since it's symmetric, that distribution of electrons around the molecule will be even all the way around. And that is basically what defines a nonpolar molecule. The distribution of electrons around the outside of the molecule is the same all the way around it. And if it's the same all the way around it, when another molecule that's exactly the same, when they come together, there's no difference in the distribution of electrons. So one carbon tetrachloride molecule looks like another carbon tetrachloride molecule. There's no difference in the distribution of electrons around each one. One's not slightly more negative than the other, one's not slightly more positive than the other, and so they just drift apart, leaving no net dipole. Now let's talk about dipole-dipole interactions. So that is an attraction between polar molecules, between the slightly positive side and the slightly negative side. So if you have polar molecules, we know that one side of the molecule, and that is the key, one side of the molecule will have a slightly positive charge. One side of the molecule will have a slightly negative charge. With carbon dioxide, the outside are the same, right? The outside of the molecule, we have slightly negative oxygens. Well, on another carbon dioxide also has slightly negative oxygens on the outside. So there's no difference between the distribution of electrons on either one, and so they don't really interact. But if you have something that does have a big difference, something like, let's say, hydrogen chloride. Chlorine has a much higher electronegativity than than hydrogen. So this hydrogen is going to have a slightly positive charge. This chlorine is going to have a slightly negative charge. And so when the slightly negative side of an HCl molecule comes into interaction with the slightly positive side of another HCl molecule, they're going to interact. They're going to pull together and interact with each other, because now there is a difference in charge. There's a difference in the slight positive, slight negative. They're going to interact with each other. So those molecules will orient themselves in space so that the slightly negative and slightly positive sides of the molecule will interact with each other. And that is a pretty strong interaction. And we call that dipole-dipole because you need to have a dipole on one molecule to interact with the dipole on the other molecule. Now we have a special dipole-dipole interaction that I mentioned before called hydrogen bonding. Now, hydrogen bonding in biology is extremely important. So it's important that we understand what hydrogen bonding is. These are particularly strong dipole-dipole interactions. And the reason is because these bonds are very polar. As I mentioned, they take place between oxygen and hydrogen, fluorine and hydrogen, and nitrogen and hydrogen. Those are the three most electronegative elements there are: oxygen, fluorine, and nitrogen. So what happens with these interactions is that basically these hydrogens in the middle sort of act as a bridge between two very electronegative elements. So in water molecules, so there's a single water molecule there, there's another single water molecule there, you will see that the hydrogen makes a bridge between these two very negative or highly electronegative elements, with the poor little hydrogen stuck in the middle. And so the hydrogen basically is sort of in this tug of war because it's the positive. It has the partial positive charge. And that partial positive charge actually goes up even more because it's in the presence of two now very electronegative oxygens. One that it's covalently bonded to, and the other that it's interacting with through this dipole-dipole interaction. And so the charge, the slightly positive charge on the hydrogen actually increases a tiny bit. It becomes even more slightly positive than it was. And so it makes this interaction even stronger. So we will see this interaction whenever we have oxygen, nitrogen, or fluorine bound to a hydrogen. Now, if they're not bound to a hydrogen, we don't see this. So don't be fooled by thinking that any molecule that has an oxygen, a fluorine, or a nitrogen can hydrogen bond. No. If they don't have that hydrogen there that can increase its partial positive charge, then it's just a regular polar dipole-dipole interaction. I mean, it's a strong dipole-dipole interaction, but if the hydrogen is not there, it's not a hydrogen bond. So always be on the lookout for molecules that have oxygen, fluorine, or nitrogen, and you're asked, can those molecules hydrogen bond between each other? Well, if these bonds aren't present, then they can't. Then it's just a normal dipole-dipole interaction. So you can see that this network of hydrogen bonds that builds in liquid water. Now these molecules are still moving around, but there's a lot of interactions going on. And it's this network of hydrogen bonds that's responsible for ice being less dense than liquid water. Why? Well, because in the solid phase, these molecules they don't move as much, right? And so they can't come and move around. Basically, they get frozen in this lattice. And so there's not as much space. There's actually there's more space in between the water molecules because they're sort of rigid. They can't become close to each other and move around in the liquid phase. They're basically locked with these hydrogen bonds present that are very, very specific lengths. And then when they get locked, they actually move a little further apart. And when the molecules are a little further apart, it means it's a little less dense, and they float on the liquid. Now, London dispersion force, I want to talk about that for a minute because it may be the first time you've heard that particular term. Now, it was discovered by someone named London, so gave it the name. So a dispersion force is basically when you have two molecules that have no other way to interact with each other. There's no charge, there's no polarity, there's nothing. There's no difference in the distribution of electrons between one molecule and another one. But if you put those molecules together and sort of basically, if they come into contact with each other, there can be an instantaneous production of a very small dipole because molecules or atoms or electrons are constantly moving around, right? So if I have a big bag of electrons over here and a big bag of electrons over there, and they're constantly moving around, at any instant in time, there can be slightly more electrons on this side than the other side. And this one side of that molecule can have slightly negative charge, and the other side of the molecule now will have just a slightly positive charge. And when that happens, basically that sets up the same thing in the element, in the molecule next to it. So if I have this instantaneous, very small dipole being formed, it basically forces the instantaneous dipole next to it. Because if this side becomes slightly positive, then in the molecule next to it, it will pull electrons, this evenly bound cloud of electrons, a little bit towards it and form a very small, slightly negative charge. And then they will interact. But as you can imagine, this is really, really, really weak. So it takes a lot of these interactions to form any sort of discernible phase, to get any kind of slowdown in the movement of these molecules. So like I mentioned, candle wax, you have these huge molecules that weigh like, thousands their molecular weight is like in the thousands of grams per mole. huge, huge molecules with lots and lots of electrons. So if there's a lot of space, there's a lot of potential to form these very small interactions. So basically, it takes place really with any force, only with very large molecules. And these molecules basically will have, these compounds will typically be soft in the solid phase, like butter is soft in the solid phase, right? Well, unless you freeze it or something, or have it in a really cold fridge. But at room temperature, butter is fairly soft because butter is made of fat, and fat is mostly carbon and hydrogen. It's mostly with some oxygens and phosphates or whatever in there. But for the most part, most of those molecules are carbons and hydrogens. And so it has a relatively low melting point. So you form basically what we call an instantaneous weak dipole, very weak dipole. And so that's why London dispersion force is by far the weakest interaction. And if it's the only interaction that a molecule can have, and they're very small molecules, they're going to be gases. And that's why all the gases we see are basically nonpolar, right? It's because and they're small. It's because they have this equal distribution of electrons all the way around, and they don't have a lot of surface area where they can form this kind of interaction. And so it's super, super weak. And so basically at any low temperature, they don't interact with each other, and we find them as gases. So we'll do this one, and then the other lecture examples we'll go over in the workshop on Tuesday. So let's have a look. So we want to identify the strongest attractive force in these substances. So we've got London forces, dipole-dipole, hydrogen bonding, ion attractions. So here we have an alcohol. We know it's an alcohol because it has the OH group. So, and it's bound to carbon. So it's a hydrocarbon with an alcohol group on the end. So that means we have this on one end of that molecule. And so ask yourself, what sort of interaction can this molecule undergo? Well, we know that all molecules can undergo London dispersion forces. So it's got that going for it, so it can do that. Is there a dipole-dipole interaction here? Yes, right? Because oxygen is present. Oxygen is slightly negative. This carbon is going to be slightly positive. This hydrogen is going to be slightly positive. So we have a dipole there. Okay, check that off. Can it hydrogen bond? Now remember, could only hydrogen bond if you have oxygen, fluorine, or nitrogen. We have an oxygen. Is it bound covalently to a hydrogen? Yes. Yes, it is. This oxygen has a hydrogen bound to it. So, yep, this thing can hydrogen bond. And that's actually one of the reasons why ethanol also boils at such a high temperature. Ethanol, which is just two carbons and an OH group at the end, a hydroxyl group at the end, that boils at like 80 degrees. Water boils at 100 degrees. That's the reason you're able to distill ethanol from water. You can separate them based on their boiling point. And so we can, because this is such a strong interaction, they both can hydrogen bond. The difference is water can form more hydrogen bonds than ethanol can. And so it takes even more energy to break up the interactions between water molecules than it does with ethanol molecules. So the strongest force there would be hydrogen bonding because there are no ions. If there's no ions, there is no ionic interactions. So let's look at the next one. So here we have KCl. What is KCl? Right, potassium chloride. So potassium chloride is what? Is that a covalent interaction? And the answer is no, because potassium is a metal and chlorine is a nonmetal, and so they become ions, chloride. So this is an ion, this is an ion. So already we can see that that is an ionic interaction. That's going to be the strongest one. So we're good to go with that one. Finally, let's look at formaldehyde down here, this structure at the bottom. So I've got a carbon, oxygen. This is called an aldehyde group, where you have a carbon, double bonded oxygen here, and then a hydrogen. That's called an aldehyde. And formaldehyde is like basically the smallest aldehyde there is with a single carbon. So when we look at this, we ask ourselves first, what shape is it? Because the shape of the molecule, we all know, is why certain things are polar, certain things are nonpolar. Do we have dipoles here? Yes, we definitely do, because the oxygen is more electronegative. So we have a bond dipole here. And we don't really have much of a bond dipole at the bottom, because carbon and hydrogen are basically almost the same electronegativity. So very, very weak dipole there. So basically the dipole of that single carbon-oxygen bond is going to be the dipole for the whole molecule. So it is a polar molecule. The oxygen is slightly negative, the carbon is slightly positive. That is a polar bond and a polar molecule. So we know it can do London forces because everybody can. We know it can do dipole-dipole interactions because it's a polar molecule with a dipole in it. Can it hydrogen bond? Well, it does have an oxygen. It's got an oxygen there. But the main thing to remember is that oxygen is not covalently bound to a hydrogen. The hydrogens are bound to carbon, not to the oxygen. So this cannot hydrogen bond. So the way this would bond with each other is that this slightly negative part, oxygen, would interact with the slightly positive part of another formaldehyde. They sort of would line up, slightly negative, slightly positive, slightly negative, slightly positive. And this is a liquid at room temperature based on that dipole-dipole interaction, not a hydrogen bond. So it has a lower boiling point than water or ethanol because they can hydrogen bond and formaldehyde can't. In fact, formaldehyde is becomes a gas fairly readily, and if you've ever smelled it, it's pretty nasty stuff.